Alright, welcome back. Homework 1 still, which is Maxwell's relationships. This is problem number 5. Oh, this is my favorite problem when it comes to Maxwell's relationships. Alright, it says, sound is defined as an isentropic compression wave. As such, the square of the speed of sound is equal to how changes in pressure relate to changes in volume or density. Incorporating everything you've learned in class, calculate the speed of sound in gold at 298.15 Kelvin. Okay. Now, in these, little videos and stuff, I am most likely not going to plug in any numbers. I don't bring my calculator down here. I don't bring my computer. So it is up to you to do the calculations. Okay. But, you can copy everything up to this point and just plug in the numbers and get full credit. Okay, so I'm just going to show you how to do it, but you can plug in your own numbers. So sound. So this is both a numeracy problem and a Maxwell's problem. So let's figure out the numeracy. Okay, sound isentropic. That means this is constant. Okay, this is constant. Compression. Okay. Alright, so compression. Well, compression can mean either changes in volume or changes in pressure. Well, let's think about, we have isothermal compressibility and thermal expansion coefficient. Which one of those has the word compression in it? Yeah, that's right, isothermal compressibility. And which one of these variables is in isothermal compressibility? Both of them. But which one is not in thermal expansion coefficient? That's right, dP. So dP, when they say compression, that usually means application of pressure or a change in pressure. Okay. And then we have changes in volume or density. Oh, well, it even says it's equal to how changes in pressure relate to changes in volume. But, even if I read it from a compression wave, it's going to be dP. But it says dP dV or dP d rho. Okay. So I'm either looking at dP d rho, constant s, or dP dV, constant s. Well, which one should I use? Well, I gotta look at my units, and it says it's the square of the speed of sound. Okay, well, speed has certain units. Speed. Let's keep it in SI. Meters per second, meter squared per second squared. Okay. And so pressure. Okay, pressure is pascals, which is newtons per meter squared, which is a kilogram meters per second squared per meter squared. All right. Well, I need to get rid of kilograms or moles. My density. My density can be a mass density or a molar density. Doesn't matter. But I'm either going to have meters cubed per kilogram or kilograms per meters cubed. Now, I got this kilograms. I don't have kilograms over here. I need to get rid of my kilograms. Which one is going to get rid of kilograms? Having density on the bottom or having volume on the bottom? Having density on the bottom. This is going to have kilograms per meters cubed. Doink, doink. And I got a meter there, I got a meter there, and I got second squared, and that means meters per second squared. All right. So I want dP d rho at constant s. From a numeracy point of view, dP dV at constant s would be valid. But from a units point of view, I have to use density. It's just kind of one of those fudge factor type of things. So, c squared is equal to dP d rho at constant s. All right. Nifty. So now I'm done with my numeracy. Now it's on to the Maxwell's relationships. Okay. Step 0. Do I have a funky function? Well, last time I checked, rho was not one of my fundamental main variables. I look at my cheat sheet and I don't see any rho's on there. So I'm going to declare rho as a funky function. So what are my steps with a funky function? First, I have to define my funky function. I have to figure out what simple variable do I want it to become. So density, mass per unit volume, or moles per unit volume. Well, volume is a simple thing. So I want to set my funky function, with respect to my simple variable. Now, do I have rho? No, you don't. You have a change in rho. I gotta figure out how. I gotta solve for the change in rho. Well, change in rho. I could do a derivative, which has changes. Okay, d rho dv at constant s. What's d rho dv? That's right, minus 1 over v squared. Well, and now it's algebra. I can solve for my d rho. I got a d rho, now I can just solve for it. So the d rho is equal to minus dv over v squared. And so this becomes minus v squared dv, dp dv at constant s. Okay. You might be like, well, does that look right? Well, I had to divide by a divide. Okay. But I can always check my units. I can always check my units. P times v. P times z, well, that is a energy per unit mass, or energy per unit moles, which is actually meters squared per second squared. All right, so we're on the right track. All right, so I got rid of my funky function. Do I have an HTC in the constants place? What's my next step? That's right. Do I have an HTC in the dx place? Nope. Do I have an s in the constants place? Yep. Okay, so I have an s in the constants place. I have two choices. I have a Maxwell's relationship. So do I have a Maxwell's relationship that says dp dv at constant s? Nope. 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 I don't have any. So I'm left with, that's right, cyclic rule. Okay. Now, remember how I like to set up a cyclic rule? Yes, you can use one on the cheat sheet, but I don't like that. I mean, I get confused about what's on top and what's on bottom because I'm kind of dyslexic when it comes to numbers. And so what I like to do is dp dv at constant s. So I'm trying to get this one in a constants place. Well, whenever I'm trying to get an HTC in the constants place, I want the HTC to be where? Top or the bottom, or it doesn't matter. That's right, we want it on the top. And so what I like to do is say equals big minus, because it's all equals minus 1. I got a derivative on top and a derivative on the bottom, or relationship. And ds, or whatever my constant is on the other one. Okay. So that's my first thing. Okay, now what am I going to put down here? Well, algebra, I have to make sure what's on the bottom here is on the bottom here. Okay. So what's on the bottom here? And what's on, that's a dv. Okay. What's on the bottom here is going to be what's on top over here, because it's divided by a divided by. Divided by, you get a top. Okay, so that's a dp. And then I ask myself, of the three letters, what's left? SV, SP, okay. And then I've done my cyclic rule and I get one of my points. But do not forget this guy! Don't forget the minus sign. You're going to drop it, I guarantee it, so don't do it. Be very vigilant about making sure it stays. Not just putting it there in the first place, but making sure it stays. Oh, alright. So, do I still have an s in the constants place? Okay, do I have a ds split? And do I have a ds? Yes, I do. Okay, yeah, I got a ds. Alright, so I have a ds. What do I do when I see a ds? I have two choices. I can do a Maxwell's relationship. Okay, ds dv at constant p. Do I have a ds dv at constant p? No. Do I have a dv ds at constant p? I do. Doesn't help me. No. Why not? Because s is still there. I cannot use Maxwell's relationships at this point unless it gets rid of the s or makes it that's heat capacity relationship. Okay, so that's a no-go. So what's my other option? That's right, a chain rule. Chain rule trying to get towards those heat capacity relationships. And I look at the constant to figure out where do I want to be. I got a ds and I got a p. ds and a p, boom, that's CPD, CPD. Okay, but again, how I like to do it is ds d something at constant p times d something dv at constant p. We'll do the same, and just to save some time, it's the same question down here. There is a Maxwell relationship, but it puts s back in the constant, so I've got to do a chain rule here too. ds d at constant v, d dp at constant v. All right. Oh, what did I do? That's right, I dropped a minus sign. Okay, so what is the blank? Well, it's the nose principle. You get to pick it. Might as well pick something easy, like, I don't know, T. Okay. And I can, now I'm at the measurables point, okay. So I can change these two measurables so that I can say that this part is equal to minus Cp dt dv at constant p over Cv dt dp at constant v. All right. Okay. And then I might as well combine it with my original thing. Well, first off, do I have a ds still? Okay, so no, I don't. I can go on to measurables, properties, equations, and state. But before I do that, let's combine it with what I had originally so that this becomes v squared cp dt dv at constant p over cv dt dp at constant v. Okay. Now, let's just assume for the moment that I wanted measurables. Would I be done? Yes, I would be. And then I would go on to step 6 and check my units. Cp has the same units as Cv, so those cancel out. I have a dt divided by a dt, so those cancel out. I have a v squared divided by a v, so there I got a v divided by a p, so I have a p times a v. P times a v, well, we've already established that is kind of what's going on up here, and we've already established that those are the same units up there, so I am still the right units. I'm good. I'm going to give myself a good thumbs up. All right. But I'm not measurables. I am properties. I'm not an equation of state in this case because I want it for gold. So I want this for gold. All right. So, dt dv at constant p. What's that say on my cheat sheet? Where's my cheat sheet? I have a dv dt at constant p, which says it is... no. I just have a positive. So, this is 1 over beta v, and this one is kappa over beta. Right. Oh. So, equals v squared cp... 1 over beta v over CV kappa over beta. Alright? Volume cancels out with that volume. That beta cancels out with that beta. So I have CP over CV times volume over kappa. But is volume a property? No. So I convert that to density. CP over CV kappa rho. Is that my final answer? No! It's not. It's close. This is equal to C squared. So I need to take the square root of it. So the speed of sound of any material is the square root of Cp over Cv over kappa rho. Okay. Now again, I mean, am I in the right units? Yeah, I'm in the right units because this is inverse pressure, this is inverse volume, and it's divided by. So I'm still good. Okay. Now, this guy has a common term. I'm blanking on. He's been bad with terms, but it's usually called gamma. Cp over Cv. Gosh, compressibility maybe. I'm late. Anyways, at this point, I would plug in my values for what those things are. Now, what are they for gold? Well, that's up to you to go find. I mean, go to, remember, Google and Wikipedia are your friends. So you can find CP, you can find CV. You might be like, well, I can find CP, but I can't find CV. Where do I get CV? You can actually get CV from problem number 2. Okay. So you can get CP from problem number 2. So watch that video. You can find kappa and you can find the density. Just plug them in. Okay. But that's all it is. So let's see here. Gotta go through my steps. Got a funky function. But really, I gotta read the prompt. Gotta apply my numeracy to really find out what's going on with